All right, we are going to start today with 8.1 notes. The goal for today will be to graph exponential growth and decay functions. The first question I really want you guys to think about is I want you to figure out which option you would choose. So the first option would be, would you want someone to give you $1 million today? The other option is you'll receive a penny today, and then the second day you're going to receive 2 pennies. The third day you would then receive 4 pennies, so double it again, and the next day you would receive 8 pennies. And then just keep doubling it every day for 30 days. So I want you to think about which option you would like to choose. I'll give you guys a minute to think about that. Okay, so if you come up with an answer, I want you guys to send it to me because I really do want you guys to think about those 2 options. Option 2 is actually an example of an exponential function. So what is an exponential function? The base is a constant and the variable is going to be an exponent. Okay, so your example there would be f of x is equal to 5 to the power of x. So notice your x there is an exponent and not, multiplied by. It's taken to a power of a variable. Your non-examples are going to be like x to the 5th. Notice that that variable is not going to be in the exponent. It's the base. And so that would actually be considered a power function, which is something that we've talked about earlier in the year. The next one, this is actually the same thing as just f of x equals 9x because 3 squared is 9. So this should look very familiar to you because that's just a linear function. So it looks all complicated when we're looking at right here with the 3 squared x, but it's simple, what you guys already are familiar with. So exponential growth, you're going to have your equation is going to look at f of x is equal to a number to the power of x. That x will be the variable. And its growth when that b value is greater than 1. Now, it's not going to be 1 because if you take 1 to a power, you can multiply 1 by itself however many times you want. Your answer is still going to be 1. So it's just strictly greater than. It's never going to be or equal to, because if it's 1, then you actually just would have a graph of a straight horizontal line going through 1. It wouldn't be exponential. Okay. Now, exponential decay is going to happen when that b value is between 0 and 1. Okay. Now, it wouldn't be 0 because 0 to a power is just going to be 0. So again, you would get stuck with that horizontal line that doesn't change. Can't be 1 because we already talked about that. You will actually never have a negative b value. All right. Now, the reason why is if you took a negative number and you took it to a power, what happens if I took something like this? Your answers are going to be alternating between positive and negative numbers, and you're not going to get a consistent graph. It would be a very messy thing to do. So b will never be negative. So let me just go and erase that, but we are going to put that as a side note here. An asymptote, we have not really focused much on this yet. We may have brought it up in previous units. But an asymptote is just a line which the graph is going to approach, but it's never going to reach that line. So when we graph it, we always graph it as a dashed line. and you'll be able to see that the line is going to be approaching it, but it's never going to actually reach that line. All right, let's go ahead and we're going to move down to actually starting to graph exponential function. So let's see. The parent function is just going to be, remember that parent function is the most simple form of a function, so get rid of anything in the beginning, get rid of anything at the end, any adding, subtracting, things like that. You want to make it the most basic version of that function that still has the part that makes it exponential. So the part that makes it exponential, remember, is the fact that that x is going to be an exponent. And so what we're going to do is we're going to eliminate everything else and we're going to look at just the parent function. What is that number that's being raised to the power of x? Notice though, because our parent function does have b in it, as I put here, that each of your parent functions, it's not just going to be the same function every time. It's going to be a little bit different. It might be f of x equals 2 to the power of x, like we have in this example. It could be 3 to the power of x or 4 to the power of x. So every single time you're going to have to try to figure out what is the parent function and then go from there. Okay. So this is our first one that we are going to graph. F of x equals 2 to the power of x. And so we're going to go ahead and do, okay, so what is 2 to the power of negative 2? Well, this is the same thing as 1 over, there we go, 2 squared. Can't really write this small. Well, 1 over 2 squared is actually, I'm just going to erase this so that we can fit it. It's just 1 over 4, okay? This one would be 1 over, this is 2 to the negative first, which is 1 over 2, which is just 1/2. Anything to the power of 0, okay? 2 to the power of 0, 3 to the power of 0, anything to the power of 0 is what? 1, okay? No, it's not 0, okay? We have 2 to the first power, which is 2, 2 squared, which is 4, 3 squared, which I am doing this all wrong. Let me back that up. Not all wrong, just that last one. All right, so let's see. This one is going to be 2 to the third power, which is 8. All right, so notice we have 2 as your base every single time. That exponent goes from negative 2, negative 1, 0, 1, 2, 3. We've calculated all those, so now we have this first coordinate point is at negative 2, 1, 4. So we're going to go ahead and we're going to put some numbers here on our graph. 1, 2, 3, negative 1, negative 2, negative 3. All right, I'm always gonna plot that first one first, so I guess I need a y-axis on here. 1, 2, 3, 4, 5, 6, 7, 8. Good. Oops. Erase that. There we go. Just checking my scale there. A little something on there. Okay, there we go. Now we just have to graph those points there. So negative 2 is at 1, 4. So if that's a half, that's going to be a fourth, right halfway in there. This is not easy to graph on this thing. All right, so negative 1 is at 1/2, which is right on, there we go, that line there. 0 is at 1. Probably that one I should have graphed first because that one's going to be the good one. 1 is at 2. That's a nice, easy one to graph. The rest of these are going to be a lot easier when you're not graphing those fractions. It looks like 8. That's a 3, 8 is our other point there. Okay. Once you have this graphed, we want to look at, okay, so where is this graph going in both directions? And what's going to happen here is if you look at these numbers here on your x, that you're plugging in for x, you could keep going this direction. You could take 2 to the negative third power, right? You'd have 1 over 2 to the third, which is 1/8. You could do it to the negative fourth power. They're just going to be creating these fractions. Okay, so your x will actually continue this direction. Okay, you could go all the way to negative infinity in that direction. How about in the direction going this way? Can you plug in 4? 2 to the fourth. Yep, you're going to get 16. Keep going. It works going in this direction also. So since you can go in both those directions, our domain here is x as an element of all real numbers. Or you could write it as x as an element from negative infinity to positive infinity like we have in the past. Okay. All right, now let's take a look at our y values, because we know that we're going to keep going to the left and keep going to the right on our graph. So what happens as we were to go to the left on our graph? And you'll notice, remember we said that negative 3 would be at 1/8. Well, what's happening is you went 1/2, 1/4, 1/8. Notice the pattern. The denominator is getting larger. 2, 4, 8. The next one's going to be 1/16. So these fractions keep getting smaller and smaller and smaller. And so when we go to connect these lines on our graph, what's actually going to happen, this one increases. This is not going to continue to decrease. Those fractions are going to get really, really small. They are going to get really close to 0. They will never reach 0 though. Okay? So they're going to be approaching 0, and that's where that asymptote comes in. So that means we have a dashed line that's actually the x-axis. That is your asymptote. So how do we write that asymptote then? How do you write the equation for a horizontal line? Y equals, and then what number on the y-axis is it going through? It's going through 0. So y equals 0 is how we're going to write that. Your range. Okay, so what y values do you see that are graphed? Now notice, you're never negative, okay? So we're never going to go down here on our y-axis. The very first one is a number that's super, super close to 0. Remember, it approaches 0. It's never going to reach 0. It's hard to kind of show on your graph because the lines get so close you almost can't see. But if you were to zoom in, you would see there's a little gap there. So it's everything above 0, right? Your y values are going to stay above 0. So how you can write that is your f of x has to be greater than 0. It's not greater than or equal to because it never touches 0. Okay? The other way you could write it is you could write f of x as an element from 0. Hold on. There we go. To infinity. Remember, it never quite reaches infinity, which is why you're going to have that parenthesis there. It also never reaches 0, so that's why you're going to have a parenthesis. It never reaches it, okay? It's going to approach it, never reaches it. Remember, it's a bracket if it were to touch 0. All right, let's go ahead. We're going to move down. We're going to talk about transformations. So these transformations, these rules, are exactly like all the other rules that we have. So let's look first at what this actually looks like. You can have a multiplier A in front of that growth factor. And I forgot to write that up at the top, so we can also write that in. We were talking about B earlier. B is sometimes considered what we call the growth factor. We'll write that in. So you have your growth factor there. You have a multiplier, the A out front. That's going to take care of vertical stretches, compressions. It's going to make a change whether or not that graph is going to flip over the x-axis. So remember, it flips upside down. We've talked about that before. The H1 goes with your horizontal, so the part that's within the variable, just like before it was inside parentheses with the variable. So when it's x minus h, it goes right. X plus h, it goes to the left. Okay, the thing at the end, it tells you whether it's going to go up or down by how many units. So all of these horizontal translations, vertical translations, and that A value, they're all the stuff from the past. Okay, we've done all this before with other kinds of graphs. If A is positive, either your graph's going to look like this or it's going to look like this. Okay, either way, it's going to be above that x-axis? Well, it kind of depends because you would have some shifts. So it might be below, but it's not going to be, we're going to see what it's going to be like. But so it would look like one of those, where if it flips, what's going to happen is it could look like this or like this, okay? And so it just, if the A is positive, it's going to be above an asymptote. I guess we could say that because it's not always going to be at the x-axis. So if A is positive, it's going to be above the asymptote, whereas if A is negative, it would be below the asymptote, because if it's negative, what happens is it flips over the x-axis. That's what we have there, okay? You're going to stretch it when your A value is bigger than 1. So again, if your A value is 1, then it wouldn't be written there because we don't write times 1. It's kind of silly to do that. But when it's larger than 1, anything bigger than 1, what's going to happen is you're going to stretch it. If it's between 0 and 1, then you are going to compress it because you're going to be multiplying by something like 1/2 or 1/4 or 2/3, things like that. All right? All right, so now we're on to the next page here. Let's see. So the very first example we have is actually a parent function. So when we go to do 3 to the power of -3, we have 1 over 3 to the third. 3 to the third is 27. This chapter, what you're going to want to get out is your powers chart. Okay? From last unit, if you have that powers chart, it's going to make this a lot easier. 3 to the third we know is 27. Because it's a negative exponent, you're going to put it down below. In the denominator, you have 1 over 27. Okay, 3 squared is 9, so that's going to be 1 over 9. 3 to the first is 3, so this is going to become 1/3. Anything to the power of 0 is just 1, so that's going to be 1. 3 to the first is 3. Then we have 9 and 27. And I did those very quickly because I already took 3 to the first, 3 squared, and 3 to the third. And from there, all you have to do is go right ahead to graph it. So let's see here. I'm going to put my x-axis here. No, I don't want to put my x-axis there. Ooh, this makes it much easier to erase though, doesn't it? Put my x-axis here. Put my y-axis there towards the middle, since I'm going from +3 to -3. Sorry, I don't have a straight edge with this. Drives me crazy, but I know you guys are probably okay with it. All right, there we go. I'm going to go up by 2's here. So 2, 4, 6. There's 8, 12, 14, 16, 18, 20, 22, 24, 26, 28. There we go. So now I can fit that 27 on there, unlike the notes that I had already done for you. Okay, so let's start graphing these. 0, 1. I always like to plot that 1 in the middle first. And then from there, that's 2, so half of it's 1. -1 is at 1/3. Oops. These I know are going to be super hard to plot because they're such small fractions. Just do your best, okay? 1 is going to be at 3, so halfway in that one. 2 is at 9, so halfway there. And then 3 is up here at 27. Perfect. And then we're just going to do as best we can to connect those points. Then we have that nice exponential growth. Remember how I was mentioning before that B value, which in this case our B value is 3, would never be negative, okay? If you were trying to do this, what would happen is every other one would be a negative number. And so if you tried to take -3 to the power of x, your answers here, and I'm only going to do it for the positive because it's going to be, this would still be 1, but this would be -3, this would be 9, and this would be -27. And so what would happen is your graph would go from positive to negative, and you'd be jumping around. So then how would you graph it? You would have like here, 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 and that would not be okay. So that is, I just wanted to show you why that B value can't be negative, but I'll go ahead and get rid of all that because, well, that's just confusing, right? So your b value is always positive, makes it much easier. All right, so let's talk about the domain and range. Again, your domain and range, this graph continues to the left, right? We could keep going to those really small numbers. We could keep going to the right. It's just going to get really, really big. Over here, it's going to be way off that chart, okay? So your domain here is x as an element of all real numbers. Your range, the range, your y value is here. We keep going up. You can see that it keeps going up. However, it does not keep going down. It's getting really, really close to zero. I mean, it does technically go down, but just by smaller and smaller amounts, it will get closer and closer to zero. It's never going to reach zero. So your range is f of x is going to be greater than 0. Okay. You could also write this f of x is an element from 0 to infinity. Okay. Your asymptote, I didn't graph that in there yet, but we have this horizontal line. We make it so that it's dashed. Okay, and that line is y equals 0. So there is our asymptote. All right. All right, so now for the harder type of example where this example no longer is just a parent function. You're going to have an a value that's a multiplier. You're going to also have a shift. So this is where we come up with Mrs. Fox lingo of the parent function comes first. That's not a Mrs. Fox lingo. The Mrs. Fox lingo is saying the sibling function and then the baby function. All right, so here we go. On this one, you're first going to talk about the parent function. So let's see. Your parent function is the most simple form of the function. So let me get a pointer here. This 4 is what has the exponent to it. Okay, so you're going to ignore the a value, ignore the h, and the k. And the only thing you're going to consider here is 4 to the power of x. All right, that's your parent function. So 4 to the negative third is 1 over 4 to the third, which is 1 over 64. Right? 4 squared is 16, so this is 1 over 16. 1/4, 1, 4, 16, and 64. All right, so then when you go to the sibling function, the sibling function is next. The sibling function is when you consider the a value. So this one is f of x is equal to -2 times 4 to the power of x. Okay, so what you're doing, that's your vertical stretch. So you're going to multiply y by -2. Okay. All right, so you're not going to do anything here with your x values. They remain the same. But your y values, you're going to multiply everything by -2. So now you have -2 over 64, which is actually -1 over 32. And don't forget to reduce those fractions. Okay, so then in order to do the baby function, which has the translation also, this one's going to go right 1 up 7. So that vector is 1, 7, meaning you are going to add 1 to all of your x values and add 7 to all of your y values. And if you want to use a calculator, that's fine, because the decimals might be a little bit easier for you to graph. And that's what we're actually going to graph, is that function there. In order to figure out your domain, range, and asymptote for that final function, what you're going to want to do is think about the domain, range, and asymptote for the parent function and the sibling function also. So your domain over here, just like the other parent functions, your domain for that parent function is always going to be all real numbers. So then those are your x values. So what did you do for your x values from the parent to the sibling? So you didn't do anything there, so your domain for that sibling function is still going to be x as an element of all real numbers. And then when you got to the baby function, the x values, you added 1 to them. But since they're all real numbers, and if you add 1, it does not change anything. So the domain is still going to be x as an element of all real numbers. All right, now let's look at your range. So originally on that parent function, we had talked about your range was going to be anything above 0. So y would be greater than 0. And then what you did when you went from the parent function to the sibling function, you actually did something to your y values there. So when you multiply by -2, this was originally going from 0 to infinity, but negative is going to flip it. So now you're going to be going from -infinity to 0. Or remember, when you multiply an inequality by a negative number, your sign flips. So now we're going to be reading y is less than 0, or going from -infinity to 0, depending on which notation you prefer to use. All right, so now that we have that for the sibling function, when we get to the baby function, you added 7 to all of your y values. So since that is considered what you're doing to your y, you're going to go ahead and on the range, you're going to also add 7. So now we're at y is less than 7. The other way to write it would be, and you can use y or f of x, it doesn't really matter. F of x is an element from -infinity up to 7. And then that also tells us where our asymptote is going to be, because you can see that since it's approaching 7, we know the asymptote is that horizontal line. So this should be at y equals 7, but I'll show you how to get that from starting with the parent function. The asymptote on your parent function was y equals 0. When you multiply that to get to your sibling function, your asymptote didn't change, because when you multiply by 0, nothing happens. You're still at y equals 0. Since you are dealing with a y equals equation, you have to deal with what you did to the y values, and since you added 7, your final asymptote for the baby function would be y equals 7. All right, so here's my graph so far. I have my axes, and I went ahead and put my asymptote on there because I know that my points need to approach that. So let's see, -2 is very close to that. And again, I don't have a straight edge, so it's not the best, but it'll do. And these are all above, between that x-axis and the asymptote, and I get that these are very hard to make accurate when you have such a large scale there, so no worries about that. And there's your graph.